Next, how to get useful products from metal ores and rocks. Many useful products can be extracted from the ground by physical separation processes like filtration, evaporation, crystallization and distillation. This clip explains how we get salt from a salt lake using evaporation and crystallization.
This is the Great Salt Lake in Utah, and surprise, surprise, it contains lots of salt. Local industry takes full advantage.
I'm at the Great Salt Lake Mineral Corporation, and their business is salt production on a very large scale.
A section of the lake has been divided into a huge patchwork of ponds, all very shallow. Salt water from the lake is pumped into the ponds down a canal. The pump itself is encrusted with salticles. As the drops of water evaporate, they leave behind tiny amounts of salt, which build up over time. The water is pumped into these huge ponds and left for many months. The sun heats it up and the water evaporates, leaving behind salt crystals. Under the microscope, you can see this happening. It's called crystallization.
The same thing is happening on these ponds, but on a much larger scale. The sun heats up the water and it starts to evaporate, leaving the salt solution to get stronger and stronger. Eventually, it becomes saturated. The water just can't hold any more salt in the solution, and the salt starts to crystallize out.
Here's a question about separating materials. Someone has mixed some iron filings and copper sulfate powder together. How could you get the copper sulfate back out of the mixture? This is one way of doing it. If you add the mixture of substances to a beaker of water, the copper sulfate dissolves and the iron filings don't. You can then filter out the iron filings, or use a magnet. Finally, you evaporate the water to get back the solid copper sulfate crystals. Unreactive metals like gold and silver are found as small particles of the pure metal, and they can be physically separated from other substances. Most metals are too reactive to be found in their pure form. They exist in the Earth's crust combined with other substances as rock ores. Ores are often metal oxides, or compounds that can be changed to oxides, from which the metal needs to be chemically separated and purified. The more reactive the metal, the more difficult it is to extract. There are two common methods of extracting metals from their ores: chemical reduction and electrolysis. First, chemical reduction. Ores found in the Earth's crust are often oxides or compounds which can be changed to oxides. In order to extract the metal in its pure form, it has to be reduced. That means either losing oxygen or gaining electrons. This clip shows how raw iron is extracted from the impure iron oxide by using carbon in a special furnace known as a blast furnace. Look out for the reduction process.
The carbon will react chemically with the iron ore, taking the oxygen out of the iron oxide and leaving crude iron. Air must be blasted in to generate high temperature, and limestone added to combine chemically with clay minerals in the ore. The product, a molten slag, separates from the molten iron and floats on top.
Iron oxide ore, coke and limestone are fed in through the top of the furnace. The coke is ignited and hot air is blasted in from the bottom through the furnace. In principle, the carbon in the coke reduces the iron oxide to give carbon dioxide plus iron, which runs to the bottom of the furnace. In practice, the chemistry is a bit more complicated than that. The limestone is added to remove the impurities as slag. Another way to extract products from metal ores is by electrolysis. This clip shows how aluminium is extracted from aluminium oxide in the form of bauxite.
Bauxite contains aluminium oxide, the raw material for aluminium production. The first thing they have to do is get rid of the impurities which give it that red colour.
The bauxite disappears into a bewildering array of pipes and vessels. Nothing will be seen of it for several days. After 4 days, it emerges, transformed into swirling crystals of aluminium oxide.
But it still needs to be dried.
At 1200 degrees Celsius, all chemically combined water is driven off, leaving a dry white powder, alumina.
Alumina is pure aluminium oxide. Getting shiny metal aluminium out of alumina is difficult and dangerous in the laboratory. So it's easiest to see what's going on first in a demonstration using another white powder. This is lead bromide, and the 2 black rods are electrodes made from carbon. They're connected to a power pack. The circuit also includes a light bulb. As soon as a current flows, it will glow. But for now it's dark because lead bromide doesn't conduct electricity at room temperature. Alumina is the same, but heat it up, melt it, and everything changes. Now a current starts to flow. Bromine bubbles off at the positive electrode, and near the negative electrode, molten metal sinks to the bottom. Extracting aluminium from alumina is very similar. It just needs a lot more heat and a lot more electricity. The pot line is the heart of the production process. It's a row of electrolytic cells. They call them pots for short. Inside, they keep alumina hot and molten with massive electric currents.
Currently, the pot lines are running at 163,000 amps. In a day, we use enough electricity to power a small town.
All that electricity does 2 jobs. First, the electric current heats the aluminium oxide. Heating breaks the strong bonds between aluminium and oxygen. That leaves positive aluminium ions and negative oxygen ions floating in the mix. Next, electric charge draws the ions apart and neutralizes them, turning them into aluminium metal and oxygen gas. Here's where the charge comes from: carbon electrodes. 16 cathodes line the bottom of each cell. Up above them hang the anodes, positive electrodes. It's a big job to replace them, but it has to be done often because the anodes get burnt up when the cell's working. Here's what happens. The massive electric current passes between the anodes and the cathodes through molten alumina. The current keeps it hot. To save electricity, they also add a material called cryolite. It brings the melting temperature down from 2000 to 950 Celsius. Alumina is made from positive aluminium ions and negative oxygen ions. When aluminum melts, the ions are free to move. They're no longer stuck together and can go their separate ways. Opposites attract, so the positive aluminium ions get pulled down towards the negative cathode. They pull electrons off the cathode, neutralizing their electric charge. That makes them aluminium atoms, not ions, so they collect on the bottom of the cell as aluminium metal. Meanwhile, the negative oxygen ions get pulled up towards the positive anodes. There, they give up electrons, neutralise their charge and turn into oxygen gas. But not for long. The oxygen reacts immediately with the hot carbon anode to make carbon dioxide gas.
So the heating process first separates aluminium oxide into aluminium and oxide ions. The electrolysis attracts the positive aluminium ions to the negative cathode, where they become atoms of aluminium metal, and the negative oxide ions go to the positive anode to become oxygen gas.
Each one of these cells produces more than a ton of molten aluminium every day. They suck it out with a machine like a giant vacuum cleaner. They skim off impurities called dross. Then they make it into ingots. These ingots are like blocks of chocolate that get shipped out to customers. Customers then remelt the ingots to cast useful products.
Different methods are used to extract metals depending on how reactive they are. The least reactive metals, like gold and silver, occur naturally. More reactive metals can be extracted from their ore by the reduction of their oxides. The most reactive metals need electrolysis to extract them from their ores. That's the end of the section on useful products from metal ores and rocks.